Here, what we have is a chart of data, and we're looking at the planets. Mercury, Venus, Earth, Mars, Jupiter, Saturn. And we've got two variables for each of these different planets. One is the mean distance from the sun. Now, these are in astronomical units, and according to astronomical units, the Earth is defined as 1.0 units from the sun. So however large that is, we're going to consider that 1. So the planets that are closer to the sun, of course, will have distance from the sun that is less than 1. And the planets like Mars and Jupiter and Saturn that are further from the Earth to the sun will have distances that are greater than 1. So there are our distance, with Earth being 1. That's our x. Here, as I plot it, that's my x, or horizontal axis. Y, or the dependent variable, is the period. Now, you can imagine that the further you are from the sun, the longer it takes to do one full revolution around the sun. That's the period. How long does it take to go around the sun? And the period will be measured in years. And so the Earth is defined as 1 year. That's how long it takes us to go around the sun. Obviously, it's 1 year around the sun. Well, if you're closer to the sun, then you don't have to wait a full year before you travel around the sun. And if you're further than the Earth from the sun, then it's going to take you longer. It's going to take longer than 1. Take a look. It's 29.4 years for Saturn to make one full revolution around the sun. So we might expect, it's a linear relationship. The further you are away from the sun, the longer your period. But when we graph it, I get something like this. This is clearly not linear, where I've graphed the period in years in the y-axis and the mean distance in astronomical units from the sun on the x-axis. The important thing for this graph here, when I graph x and y, so this is a point, this is a point, an xy point, an xy point, an xy point. I don't get a linear relationship. I clearly didn't have a linear relationship when I graphed mean distance and period. So one of the things you'll see in statistics, and I encourage you all to take that statistics course, is if you don't find a linear relationship with the two variables, you can take the natural log of each of the variables, or the natural log of one variable, or the natural log of the other variable, or the natural log of both of them. When I take the natural log of both the mean distance, x, and the period y in years, I come up with these. Now, each of this is Mercury, x and y, natural log x, natural log y. Venus, natural log x, natural log y. Earth, notice Earth goes to 0. Mars and, that's Mercury. This is Mars and Jupiter and Saturn. So each of these is an XY point. If I look, here's an XY point, here's an XY point. For each planet, I'm going to get an XY point. And when I graph them, I do get this straight line. And now, obviously, I can come up with a model here. Because I saw a linear relationship between the natural log of my independent variable and the natural log of my dependent variable, what I'll do is I'll just pick 2 points. Now, Earth is at 0, 0, so that's a convenient point to pick. So I'm going to choose this point, and Mars is right next to it, so why not? They are all linear, or they appear to be linear at least, so it doesn't matter which 2 points I pick. I picked Earth and Mars, and I know that slope is y2 minus y1 over x2 minus x1, and when I crunch the numbers, I get about 1.5. That means y equals mx plus b. But we saw that we're going through the point 0, 0, so our y-intercept is 0 there. Our slope is 1.5, so we'd say y is equal to 1.5 of x. But of course, we don't have y and x. We took the natural log of y and the natural log of x. So that would be our final model for this, that the natural log of y is equal to 1.5, the natural log of x. Of course, you could do this on your calculator too by entering all of these original data points, taking the natural log of each of them, and then coming up with the regression line. You'll do much more of that in that statistics class, but it's just a little taste of it right now.